2013 Canadian Open Mathematics Challenge Part B. Given a triangle ABC, x and y are points on side AB with x closer to A than y, and z is a point on side AC such that xz is parallel to yc and yz is parallel to bc. Suppose ax is 16, xy is 12, determine the length of yb. So we have a situation where we have several triangles, and that is parallel to that, and that line is parallel to that line. So we're going to have some similar triangle situations. So the first one is triangle AYZ is similar to triangle ABC, because ABC is the big one and AYZ is this one. So because of the parallel lines, these two triangles will be similar since they have the same angles. So using the ratio of the sides, we get AY over AB is equal to AZ over AC. Now let's substitute in what we know. AY is, let's see here, 28, since we're adding 16 and 12. And then YB, that is what we have to figure out, right? Okay, so I'll just label that something. Let's just call it A. So that means A to B will be 28 plus A. AZ is 16. Actually, no, AZ and AC, we don't know yet. Okay, so we have to come back to that later. Okay, well, at least we got that far. We have another similar triangle situation. That triangle AXZ is similar to triangle AYC. So AXZ is this guy, and AYC is the bigger one. They are similar because they have the same angles, because these two lines are parallel. Okay, so from that relationship, we get that AX over AZ is equal to AY over AC. So AX is 16, and we have AZ. AY is 28 over AC. And therefore, if we mix this around a bit, we get AZ over AC is equal to 16 over 28. Okay, so this finding is what we can substitute here. So that means AZ over AC is 16 over 28. So there we go. That will allow me to solve for A. Okay, let's do it over here. So cross multiply, I guess. So 28 squared is equal to 16 times 28 plus 16A. So that's going to be 784 is equal to 448 plus 16A. So 16A is equal to 336, and then dividing through, we get A is equal to 21. So since A was what I used to represent YB, YB is 21. There is a unique triple of positive integers ABC with A less than or equal to B less than or equal to C, and 25 over 84 is equal to 1 over A plus 1 over AB plus 1 over ABC. Determine A plus B plus C. Okay, I think this is one of those questions where you just have to use trial and error. Let's see what happens. So 25 over 84. Let's get a common denominator here. Multiply top and bottom here by C, and top and bottom here by BC. And that would give me BC plus C plus 1 all over ABC. Now if I just do a direct comparison, I will get 25 is equal to BC plus C plus 1, and 84 is equal to ABC. Well, let's see what happens. Remember, it's a math contest, so we don't have too much time to fiddle around. We have to get sort of a general sense if we can do this or not. 84 divided into its prime factors is 2 times 2 times 3 times 7, and that is going to be A times B times C. So let's see what we can get. Keeping this in mind also, that's also very important, because I can make this work pretty quickly, but it will not satisfy that inequality, unfortunately. All right, so let's see. Let's say C is equal to 7. And then let's say B is equal to 6. I'm just sort of getting a feel for it. And then A would be the 2. Let's see what happens over here. This would be B times C, which is 42, plus 7 plus 1, and that's 50. Okay, well, that's obviously not equal to 25, so that doesn't work. And then when you continue to fiddle around, you'll find that there's no solutions. There's nothing you can do to make this work. Okay, so what does that mean? Does it mean that the question has no solutions? No, it just means that these scenarios have no solutions. But when I got this 50, it immediately made me, that little alarm or that light goes on in your head that, hey, I don't need to work with this. I can work with something that's equivalent. I can work with 50 over twice the 84, which is what, 168. Because that is the equivalent. So let's work with that. I think that will be much more helpful. So now that means I'm making 50 equal to BC plus C plus 1, correct? And let's see, what else do we have here? 168 is now equal to this ABC. Okay, this could work. Let's see what happens. Well, again, I'm going to sort of use the same kind of tactic that break it up into prime factors. So 168 is 2 times 2 times 2 times 3 times 7. And let's just see what happens. So C, I'm going to choose 7. Because remember, I've got to keep this in mind. That's actually a very important aspect of the question, that we got to make sure that inequality is satisfied. 6 will be my B, just like as before. And then this time, I've got a little bit more than before. I can't make it a 2. I've got 2 2's left over, so A will be the 4. And let's see what happens. First of all, 50, B times C. Well, this is going to be exactly the same as before. 42 plus 7 plus 1. So it indeed satisfies that. But then what happens with the ABC? Well, the ABC is exactly what I did before. It's just this time it satisfies 168. Correct? So ABC is 7 times 6 times 4, which is 42 times 4, which is 168. So 168 is equal to 7 times 6 times 4. So there you go. So with a little bit of fiddling around, you get it. It's actually not that bad. So they want A plus B plus C. Okay, that's not so bad. So 7 plus 6 plus 4, which is 17. So there you go. So the key to this question, of course, was to first assess the 25 over 84 and realize that you're not going to get it to work with a little bit of fiddling around with those numbers. And then you can say, well, I'll just make it into something that is the equivalent, but not fully reduced to lowest terms, which in this case was 50 over 168. And the clue to get that 50 was obtained by fiddling around with this 25. So that's the approach that I had to this question. Teams A and B are playing soccer until someone scores 29 goals. Throughout the game, the score is shown on a board displaying 2 numbers, the number of goals scored by A and the number of goals scored by B. A mathematical soccer fan noticed that several times throughout the game, the sum of all the digits displayed on the board was 10. For example, a score of 12 to 7 is one such possible occasion. What is the maximum number of times throughout the game that this could happen? Okay, so we've got Team A, let's say, and Team B, and this is the score. And so, for example, they gave us 12-7. When the score is 12-7, the sum of the digits are 1 plus 2 plus 7, and that is indeed 10. Correct? So that is just an example that they gave you to show you how this works. Now, the key to this question is a very important point, that the sum of the digits on the scoreboard is 10. So that means that the sum of the scores must be one more than a multiple of 9. So let me write that out first. So, for example, the sum of the digits on the scoreboard are 10 here. The sum of the scores, well, in this case, 12 plus 7 is 19. And that is indeed one more than the multiple of 9, because 19 is equal to 18 plus 1. And 18 is a multiple of 9. It's 2 times 9. So this is, I think it's actually quite challenging to come up with this conclusion. It's a difficult question. But if you do come up with this, it helps. So let's move forward with this piece of information. Okay, so we've come to this great conclusion. Now we have to figure out how to move forward. Okay, well, they tell me that the game ends when 29 goals are scored, right? So the highest possible score on the board could be 29-28, right? Because the game ends when one team scores 29. And then, of course, the lowest score on the board is when the game first starts, which is 0-0, of course. So the sum here is 0. The sum here is 57. So the sums range from 0 to 57. So the sum of the scores must be one more than a multiple of 9. So we have to look at multiples of 9 and then one more. So first, multiples of 9. Multiples of 9. Well, obviously we have 9, 18, 27, 36, 45, and 54. Correct? Now we want scores, the sum of the scores. The sum of the scores. And those are going to be one more than a multiple of 9. So those will be 10, 19, 28, 37, 46, and 55. Okay. So now we need scores to occur in a single game. This is another very important point. Need the scores to occur in a single game. So what that means is that certain scores will not be possible. So let's just start off, and hopefully this will make sense. So we want the sum of the scores to be 10. Okay. So what could a score be? Well, we have several possibilities, right? 0, 10, 1, 9, 2, 8 so far, and so on. But if you make it like that, you will not be able to have all the scores occur in the single game. So we can really only use 5, 5. And it'll become clearer once we kind of proceed with the question. Now let's get to this. How can we make a score of 19? Again, many choices, right? But remember, we're already at 5. So we can't go lower than 5. We can go higher than 5, but we can't go lower than 5. So if we stay at 5, then this next score has to be a 14. That's the only way. So as you can see, you say, well, let's go back to here. What about a score of 4, 6? That would total 10. Never be able to get a score of 5, 5, because if a score is 4, 6, this team has already scored 6 goals. You cannot go to then a score of 5, 5 because the score can never go down by 1 goal, right? So that's the tricky part of this question, is we have to try to get everything to fit into one game. And then we go to 28. We've already scored 14, so we can't go lower than 14. So if we keep 14 as the score for that team, this has to be therefore 14, because 14 plus 14 is 28. Then we get to 37. Well, same thing. This team has already scored 14 goals, so we have to keep it at 14, but the other team can go up, and it goes up to 23. Now we're up to 46. Again, this team has already scored 23, so we cannot go lower than that. So therefore, this team has to be 23 in order for 23 plus 23 to add up to 46. And then finally, 55. 55 is a problem because we're already at a score of 23. How do we get 55? Well, 55 is a score that is obtained in two ways, right? You can have, say, the highest is 29. So 29 and 26. That's one way of getting 55. Another way is 28, and that would mean 27. That's also 55. Now you might say, well, we can keep going, right? What about something like 25 and 30? That gives 55. But you can't get 30 because the score ends, the game ends when somebody scores 29 goals. So this is not possible right here. So these are the only two to get 55. But notice the sum of the digits will not be 10. The sum of the digits here would be what? 2 plus 9, which is 11, plus 2 plus 6, which is 19. Sum of the digits. Similarly here, the sum of the digits looks like 19 again. So this one has no solutions. So the only solutions we actually get that work and fulfill the criteria of the question are 5, 5, 5, 14, 14, 14, 14, 23, and 23, 23. So when they say, what is the maximum number of times throughout the game that this can happen? It's 5 times. And the key is that it all happens in a single game. So other scores cannot be included because you cannot go down in the value of the number of goals being scored. Let a be the largest real value of x for which x to the power 3 minus 8x squared minus 2x plus 3 is 0. Determine the integer closest to a squared. This has a cubic root, x to the power 3. So it would have 3 roots. Now, those 3 roots I will call A, B, and C. Now, I don't know what those roots look like, so let me just make a rough estimate. And like I say, you can kind of see that when x is very large, it will just keep going up like that. And when x is very small, it'll just keep going down like that. So somewhere in the middle is going to be the roots. So let's just say we have to figure out what the roots are manually. We do that by substituting certain values into here and getting an approximation. So we start off, let's figure out the value of this. Let's say f at x is equal to this, right? Which is x to the power 3 minus 8x squared minus 2x plus 3. So let's see what we can get. If you fiddle around and we get f at -1, it will be -4, which is less than 0. And then if you keep going, you can get f at -1/2 is about 1.875, which is greater than 0. So that means that, and I'm going to exaggerate this a bit, if this is -1 and this is -1/2, right? Right here. Then -1 is -4, which is somewhere down here, and -1/2 is somewhere up here. So obviously the graph crosses the axis between there. So the first root is somewhere in there. Okay, so we'll just put that in for now. And then we keep going like this. We keep kind of approximating. Let's try f at half. When you plug in that, you get about 1.25, which is obviously greater than 0. And then f at 1 drops down to -6, which is less than 0. So that means that, again, when you're here, it'll be up here somewhere. Well, not that high, but somewhere here, I guess. And then when it's 1, it's dropped down to here. So again, whatever this graph looks like, I have no idea, but it's obviously going to have this kind of behavior. So there's another root right there. And then eventually, as I had previously mentioned, when x values become very, very large, it has to eventually shoot back up, because the larger the x value is, the larger the f at x value will be. So eventually, somehow, some way, it will come back up and eventually cross the axis again. So that is very approximate. So I'll label these. Now, a is the largest of the roots. So this is a right here, this guy right there. And then B and C, it doesn't really matter, so I'll just label this one B and this C. So those are my 3 roots. Okay, so that is something you do as an approximation. So we have A is the largest root. And then we have B and C. So we have B is somewhere between -1/2 and -1, and C is somewhere between 1.5. Correct. Okay. So that is pretty much the first part of the question. It's just really approximating. Now let's take a closer look at this and see what we can get. So we have x to the power of 3 minus 8x squared minus 2x plus 3 equals 0. Okay, so let's try to manipulate this a bit. I'm going to factor out the x squared, and I'm going to get x minus 8, and I'm going to put the other guys on the other side, so 2x minus 3, like that. Then isolate for x squared, 2x minus 3 over x minus 8. Now, the 2x minus 3, I will try to make it cancel with x minus 8. I can do that if it's minus 16, but of course, I've got to add a 13 to that in order for it to end up being minus 3. And this is x minus 8. So the 2 I can factor to get x minus 8 over x minus 8. And then this 13 I can kick out separately, like that. Okay, so now x squared becomes 2 plus 13 over x minus 8. Okay, so this is my left side, and this is my right side. And now what we do, so we have to approximate this again. So let's see. We have a table with x, left side, right side, and let's see what happens. Okay, so if we set x equal to, we can't set it equal to 8, so let's go in that vicinity. Let's say we try 8.1. If we try 8.1, the left side becomes 65.61. The right side becomes 132, which obviously is not equal, not even close to being equal. If we go up to 8.2, however, the left side is 67.24, and the right side becomes 67. And that's very, very close to being equal. So I conclude that x is approximately 8.2. And therefore, x, since x is a root, then that means this a must be approximately 8.2. And that makes sense because a is the largest one. So a is approximately 8.2. And what do they want? They want a squared. Well, a squared would be, I guess, 8.2 squared. And 8.2 squared is approximately, well, it's right here, 67.24. And they want the closest integer, well, the closest integer to that would, of course, be 67. Closest integer to 67.24. So 67 is the answer to this question.